Okay, good morning. So can you all see the screen?
Yeah, doctor, all good.
Okay, great. Thank you. Yeah. Okay. So last time we studied that in the transistors there are parasitic capacitors, and we said that this can have an impact on the performance or the response of the circuit and the range of amplification depending on what frequency range I'm operating in. So today we're going to go over an example of a basic amplifier circuit. And in this basic amplifier circuit, first we will solve for the low frequency response. يعني هنشوف كيف الgain we used to derive it in the typical way. And then we are going to insert a capacitor into this design and see how that affects the response. What would be VO over Vn as function of the operating frequency, and inspect it if my Vn has varying frequency, هيدي sine omega t, where omega varies from 10 to the 2 radians per second until 10 to the 8 radians per second. يعني الانput signal has a frequency omega which is varying. Okay, so هيك a quick refresher. If I have a signal, أول شيء something that we should always keep in mind is that typically my signal V sig R sig, at the end of R sig I will have Vn. يعني على طول if I'm looking for where is Rn or where is Vn, I look at the point between R sig, end of R sig and ground. And of course the output is feeding to the load Rn. Here we are saying that I'm going to replace this voltage amplifier. So this is a voltage amplifier. And just like we studied the common source amplifier or common emitter amplifier, we characterize my voltage amplifier by Rn, by Ro, and by its open circuit voltage gain. And if it is not loaded, what is its gain? And when we want to replace a voltage amplifier with its symbol, we replace it with Rn between Vn and the ground, a voltage dependent voltage source, which is AVO times Vn, and the output resistor, which is connected then to the load. So شلنا الامplifier, we removed the amplifier from the upper block and we replaced it by its model. So our first step is we want to solve for VO over Vn with no capacitors present. يعني على we're operating at the low, obtaining the very low frequency gain. Okay, so in this scenario here, VO over Vn is equal over Vs, sorry, pardon me, is equal to VO over Vn times Vn over Vs. يعني I can take the chain gain from here to here and then from here to this point. Okay, so let us solve first for VO over Vn. To solve for VO over Vn, we need to look at the output network. So I know that VO is equal to RL over RL plus RO times AVO times Vn. Okay, so to solve for VO over Vn, I start by solving for VO as function of the network here, because I know that VO is some voltage divider function of AVO times Vn. This should be clear to you, right? So this tells me that VO over Vn is equal to RL over RL plus RO times AV. Now, the second step that I want to solve for, so first I solve for VO over Vn. Second step, I need to solve for Vn over Vs. And to solve for Vn over Vs, I see that it is very clear for me here. I can use this voltage divider network here, and I can find Vn over Vs, and Vn over Vs is going to be equal to Rn over Rn plus R sig. So it's a voltage divider, it's a simple voltage divider network. Accordingly, the Vo over Vs can now be written as the product of those two gains, which is equal to Rn over Rn plus R sig multiplied by the gain of the second network, RL over RL plus RO times AV. And we are going, pardon me for the noise, and we are going to call this gain K, which is the low frequency gain. يعني undistorted gain. If there are no capacitors, only the pure circuit, I can assume that I can attempt or achieve this maximum gain. Anybody has any question how we reach to this value here? Okay, great. طب هلا we are now going to say, well, what if I have a capacitor C, يعني أنا I have my network here, V sig R sig. Okay, this is V sig R sig, and I have my output load RL. I have my amplifier as we drew it before, drawn by Rn, and this is Vn, and I have the Ro and the intrinsic gain of the amplifier اللي هو AVO times V. Now what if I tell you that we have, or we find out that we have a capacitor Cn in parallel to Rn due to the parasitics of the amplifier. So what happens if we introduce Cn due to the parasitics of the amplifier? How will my gain change? Let us see. So we would still use the same equation. This is V out is here. It's expressed here. So to find Vo over Vs or V sig, Vo over Vs is equal still Vo over Vn times Vn over V sig. For Vo over Vn, did my network change? Is it still the same or did it change? تغيرت النتورك بين هيدا this circuit that we see here and the circuit that we see here, the yellow network that governs VO relationship to Vn. Is it still the same? Can I still use the same expression?
Yes, the same.
Okay, so we will use the same, so it's still RL over RL plus RO times AV. The part that changed is now VO over Vn. I still have some form of the Vn over Vs, pardon me, I have some form of voltage division, but if I call Vn to be equal to 1 over Scn in parallel to Rn, then I can claim that Vn over Vs is equal to Zn over Zn plus Rs. يعني Vn over Vs now takes a different form. Okay, so let us derive it بس هيك to give you a refresher how we handle this. We're going to rewrite this as 1 over 1 plus Rs times 1 over Zn. Okay, so the 1 over Zn is really 1 over Scn plus 1 over Rn, and this expression I can write it as Scn plus 1 over Rn. Okay, so now if I want to write the overall gain that I will have this of the form, يعني كان عندي قبل Rn على Rn plus R sig. Now I'm going to write Vn over Vs. It is equal to 1 over 1 plus Rs in R sig. Actually, let us just differentiate بينه وبين S. R sig into SCN plus 1 over Rn. The reason I'm expanding this is because I want to explain to you later what is the compact form that we want to maintain any expression that we derive. So this is equal to 1 over 1 plus, first I put the S term alone, so this is S times, this is Cn times R sig, okay, and this is 1 plus 1 plus 1 over 1 plus R sig over Rn, okay? And this, if I rewrite it, it's going to be equal 1 over, I multiply by Rn up and down, I end up having Rn plus R sig plus S times, pardon me, Cn times R sig times Rn. هلا, what matters to us is that I have this in the form of A plus S times B, okay? And the way I want to write it, I want to write it and to factor it out such that I will have A into 1 plus S times B over A. Why do I want it this way? Because anytime I want to determine my system in terms of poles and zeros, I want to make sure that I have the denominator in the form of 1 plus S over omega 0. يعني I will start to figure out the different individual poles and zeros. So this expression, if I expand it, I will end up having Rn over A over 1 plus S times B over A. So this comes out to be equal to Rn over A was Rn plus R sig, okay, multiplied by 1 over 1 plus, let us keep the S here redded, S times, and let us see what was the B over A. It was Cn times R sig Rn. So this is Cn times R sig times Rn over R sig plus Rn. What is this quantity here?
R6 parallel with Rn.
This is R sig parallel to Rn. So my final expression comes out to be equal Rn plus R sig, okay, times 1 over 1 plus S times Cn times R sig parallel to Rn. Okay, so this is the expression of Vn over V sig. Therefore, if I look at the final term, so if I go back to the full term, Vo over V sig, it is going to be equal, let us summarize it now, it is going to be equal to RL over RL plus RO times AVO, okay, times Rn over Rn plus R sig times, we're gonna write it in the form 1 over 1 plus S over, and here we're going to call this omega 0, where omega 0 is equal to 1 over Cn into R sig parallel to Rn. Okay, let us inspect the first part of the expression. So this part here is really whatever I have derived before as K. Okay, this part here is whatever I derived before as K, which is the low frequency gain, before I introduced the capacitor. Okay, so, and this omega 0 came as a result of the introduction of the capacitor Cn. يعني هي الأوميجا 0 it happened because of the introduction of Cn. So practically speaking, I can now write Vo over V sig okay, as k over 1 plus s over omega 0. Okay, now this omega 0, it is a property of the circuit element. Side omega 0, it's a property of my circuit R and C values. It does not change with the input. It is function of the circuit elements, of my circuit elements. Okay, sorry, pardon me. It's a property of my circuit elements. Okay, so it's a property of my circuit elements, the R and C values that I have. K is also a property of my circuit elements. Okay, so if we want to look at a set of given values for this circuit, so in the slides, we tell you that we have given, okay, Rs is equal, and we'll go over the slides, 20K, R sig equals to 20K, Ri is 100K, and I'm just writing it to give you the values. Ci is 60 pico, AVO is 144 volts per volt, RO is equal to 200 ohms, and RL equal 1K. If I plug in those values into this expression, I end up finding that K, the value of K is equal to 100. هلا هنكتبها for the purpose of the expression how we will operate at different frequencies, and we will end up finding that omega 0 is equal to 10 to the 6 radians per second. Okay, so what does this mean to me? What does this imply to me? This implies that my gain, it is G of omega, or it is basically AV of omega. It is equal to 100 over 1 plus S is really J omega over 10 to the 6. And therefore, the magnitude of the gain at a given frequency is going to be equal to, in this case, 100 over the square root of 1 plus omega over 10 to the 6 squared. But also, this tells me that my gain has a phase. Okay, so there is a phase, okay, for the transfer function, and this phase, if my gain for VO over Vn is 1 plus j omega over 10 to the 6, how do we find the phase? It is going to be equal to minus arctangent of omega over 10 to the 6. Let us make a little refresher here. If I have 1 over A plus JB, what is the phase? Minus arctangent of B over A. So نحن أخذنا الإكسبريشن the 100 does not have a phase لأن its phase is 0, and the denominator here will result into minus arctangent of B over A, and A is equal to 1 here. Okay, great. So this tells me that if I am starting, that from now on, if I am starting with Vn equal to 0.1 times sine of some omega t, okay, then V out is equal to, at that specific omega, 0.1 times, and we will have here sine of omega t plus, so we're going to add to this, we will multiply this by the magnitude of AV at that specific frequency, okay, and the phase will be the angle or the phase at that specific frequency. Okay, so we'll have some angle or some term phi which is going to be added here. Okay, فإذا if we have the input operating at a specific frequency omega, the output will be amplified depending on the magnitude of the gain at that frequency and the phase at that frequency. So let us build a table here. So they told me in the given that my input is going to be equal to 0.1 sine of 10 to the 2t, and it's going to be 0.1 times sine 10 to the 5t. And just let me check the numbers that we have in the slides and then we go over them. And they also told me that I have 10 to the 6. Okay. And I have 10 to the 8. So I have different input signals. Each time I'm inputting a different input signal. And my objective is to really find VO, what it is going to be equal to. Okay. So in this scenario, first I need to find what would be the gain in amplitude, and I need to find the phase of AV. Okay, here the magnitude of the gain is going to be 100 over the square root of 1 plus my omega is 10 to the 2 over 10 to the 6 all squared, right? So the 10 to the 6 is omega 0, and my operating frequency here is 10 to the 2, so I'm plugging in here 10 to the 2, right? And this approximately, the 10 to the 2 over 10 to the 6 negligible, so this is approximately 100, right? And the phase that I am going to incur is equal to minus arctangent of omega that the input is at over omega 0. So here is my omega, and this is approximately arctangent of 0. And we can say that this is approximately 0, or we can say that if we want the exact number, we have it here in the slides, and the exact number comes, well, they assume that it is approximately 0. And so if I want now to write my output signal, so my VO is going to be equal to, okay, 0.1 times 100 times sine of 10 to the 2t plus phi. So this is going to be 0.1 times 100 plus 0. So this is going to be equal to times 10 sine of 10 to the 2t. Okay, is that clear?
Yes.
Okay. طب هلا at the other point I have now Vn is equal 0.1 times sine 10 to the 5t. Okay, so if I want to find the magnitude of AV, this time I will find it at omega equal 10 to the 5, and this is going to be equal to 100 over the square root of 1 plus 10 to the 5 over 10 to the 6, and this comes out to be 99.5, I think. Okay, and the phase of the gain at omega equal 10 to the 5 comes out to be minus arctangent of 10 to the 5 over 10 to the 6, and this comes out to be minus 5.7 degrees. طب هلا يعني هيدي it is simple, we're just gonna write the output what it looks like, but then I want to bring to your attention two more frequencies that are important. So the output comes out to be 9.95 times sine of 10 to the 5 10 to the 5t plus the phase, which is minus 5.7. Now what if my input now is operating at omega 0, يعني Vn is 0.1 times sine 10 to the 60. Now my frequency omega is really operating at omega 0. And in this example, here omega equal omega 0. Okay, so in this scenario, the gain AV at omega equal omega 0 is going to be equal to 100 over the square root of 1 هيدا عفوا square over the square root of 1 plus 10 to the 6 over 10 to the 6 all squared. So this is equal to 100 over root 2. Do you remember, does this number ring a bell for you? When the gain is divided by root 2, this really represents the 3 dB, exactly, the cutoff or the 3 dB frequency. So i.e. we are operating at the cutoff or the 3 dB frequency. So the gain will drop by 1 over root 2. If we take the 20 log, so the 20 log 10 of AV in this case will be 20 log 100 minus 20 log root 2, and this will be equal 20 log 100 minus 3. Okay, and this is where the 3 dB comes from. Okay, so this is the cutoff or the 3 dB frequency. Now, at this 3 dB frequency, the magnitude now is really equal to, the magnitude is equal to 100 over root 2. Let us see what the phase comes out to be. So the phase of AV at omega equal omega 0 is going to be equal to minus arctangent of 10 to the 6 over 10 to the 6, Li minus arctangent of 1, which is minus 45 degrees. So this is another property of operating at the, if I have a single pole, and I am operating at that specific single pole, the phase is going to be equal to 45. يعني إذا أنا my system is represented by one expression that has a dominant cutoff frequency, عندي وحدة cutoff frequency, okay? And we will explain this in more details. The phase at that specific, at the 3 dB frequency is going to be minus 45 degrees. So let us inspect what happens here, and later we will revive or refresh our memory about the Bode plots. So what happened here is that here we have at very low frequencies, okay? So when omega was much smaller than omega 0, the gain was almost the same as the low frequency gain, and the phase I did not lose much, it was 0. When I was operating at the cutoff frequency, the gain dropped by 3 dB and the phase was minus 45 degrees. And then when I am operating at a large frequency, so now when my Vn is equal to 0.1 sine of 10 to the 8t, and 10 to the 8t is a frequency which is much larger than omega 0, لأنه 10 to the 8 is bigger than 10 to the 6. Okay, in this case, my magnitude of AV at this omega هيكون هو 100 over the square root of 1 plus 10 to the 8 على 10 to the 6 squared. So notice how this term now becomes dominant, and this is like 100 over 10 to the 8 over 10 to the 6 squared, square root of it becomes 100, and so my gain becomes 1. So my gain dropped significantly. This is almost 0 dB gain, right? 20 log 1 is 0, and the angle at AV is equal to minus arctangent of 10 to the 8 على 10 to the 6 اللي هي approximately minus 90 degrees, لأنه نحن هون عم نقول minus arctangent of a large number اللي هو 100 كأنه tended to infinity. So in this scenario, my output is going to be equal to 0.1 times 1 times sine of omega t minus 90 degrees. فإذا once I obtain the expression and I obtain the magnitude and the phase of the gain, I plug in the magnitude and the phase into the expression of the output, and I can really find what my output behavior is. But what we noticed here as we were building the circuit, or as we were building the design, that the gain started high, it dropped, and it went down to 0, close to 1, and as omega increased. Okay, so this is what matters to us. I operated at 10 to the 2, I operated at 10 to the 5, I operated right at the 3 dB frequency, which is 10 to the 6, and then I operated at 10 to the 8, and as my input changed its frequency in relation to my omega 0, which exists at solely at this point, we see how the gain and the phase were affected. Okay, so this is what matters that we learn from this. Now, anybody has any question here? Okay, so what I'm going to do now, I'm going to go back to the slides and walk you through this derivation, okay, slide by slide, to resettle the information, okay, to resettle back the information into your head. And we will see if you have any questions there. So let me share the slides again, and I will share with you this derivation. Okay, so let me, 1 second, make host here. Okay, sorry. Okay. Okay, so let me share the screen now, and let us look through the slides, what happened here. So what we did today is we looked at the amplifier circuit, and in the amplifier circuit we said that this is typically how the amplifier looks like, and we're going to add a capacitor Ci here, and we want to study its effect on the gain of the amplifier. And then we said, given those values for the circuit parameters, we're interested really in checking the response of VO as function of Vn or V signal. Pardon me, I wrote Vn a lot. It should have been Vs. I will fix it in the slides before I upload them to you, as function of the operating frequency. Okay, so for the solution, we said we first study the voltage divider network, add the input to find Vn over Vs, and we end up with an expression which has a pole, definition of a pole, yani 1 over 1 plus S over omega 0, and some gain. And as far as VO over Vs, we have the gain of the outer network of the circuit. So the overall gain of the circuit can be written as the product of those terms that are independent of the frequency and a term that is dependent on the frequency. And this can be written as a transfer function in the form of K, where K is really this term here, over 1 plus S over omega 0, where 1 over omega 0 can be derived from C into RS parallel to RI. Okay? حدا عنده سؤال until here? Anybody has a question until here? Okay. So this is K, and this is omega 0, and let me erase all the ink on this slide. So this is K, and this represents 1 over omega 0. And now this acts like a low-pass filter because it's characterized by one cut of a frequency. And this low-pass filter has K equal 100 and the 3 dB frequency equal to 10 to the 6. Okay? And then we said, well, what does this mean to me? Omega 0 is really the 3 dB frequency. It is the cutoff frequency where the gain becomes the gain divided by √2 at omega 0. Okay, this is at, pardon me, at omega 0. And then we talk here about now we start to explain to you that the transfer function is really going to have a slope. Okay, so we start to talk to you about that the transfer function is going to first start with a constant gain, and then the gain is going to drop. And here, if I want to draw the gain in dB, this is going to be the 20 log magnitude of the transfer function t. Okay, so this now we will take this and look at the Bode plot interpretation of what does this mean. Let us make a refresher on the Bode plot. But first, I'm going to skip these and go over what we have explained in class, which is the solution. Given a transfer function t of s with this format, knowing that Vs can take different forms and may operate at different frequencies, what is the magnitude of the output signal VO of t? Okay, and we said that in our derivation on the chart that the transfer function can be written as the product of an amplitude and a phase. The phase is minus arctangent omega over omega 0, and the magnitude is really k over the square root of this expression here. And that the output is going to be the amplitude of the input multiplied by the gain times sine omega t plus the phase phi. Okay, so this is what we explained a little bit ago, and we said that this magnitude and this phase are going to pop up here and here. Okay, so the magnitude and the phase are going to pop up here and here. And then we started to calculate, well, if I plug in right directly into this red circle and into this here to find what the magnitude and phase will be at a specific frequency omega, here the magnitude will be 100 and the phase will be 0. And at the other omega, so at very small ones, the magnitude is really the low frequency gain and the phase is 0. So the magnitude is equal to 100 and the phase was 0. And as I increase it, I start to have some effect. At omega 0, the magnitude gets divided by root 2, so this becomes 100 over root 2, and the phase is minus 45. And this is interesting because we will see it in the phase and Bode plot soon. And at omega much larger, as omega tends to infinity and much larger, then the gain becomes equal to 1 or lower, so it drops a lot and the phase becomes equal to minus 90 degrees. Do I want every time to go through these calculations? No, that's why we introduce the Bode plot approximation of the circuit. We introduced drawing the magnitude and phase Bode plots so that we can really get an estimate or an approximation relative to the cutoff frequencies or relative to the operating frequency, the poles and zeros of my circuit. How will my magnitude and phase change? Okay, so let us now look at a basic refresher of the Bode plot, and then we will go into in-depth details, but let me give you a refresher on this. Okay, so let me share the screen again, and please stop me if you have any questions. So okay, so I will post this set of slides for you, but let us see here what we are getting on this slide. Okay, so if we have a transfer function where t is equal to 1 over 1 plus s over omega 0, we remove the constant here, okay? Then the magnitude in dB for this transfer function is going to be equal to 20 log magnitude of t, and this is if we take the upper and the lower terms, the magnitude of t, we said that it is equal to 1 over root 1 plus omega over omega 0 all squared. This means that the 20 log magnitude of t is going to be equal to 20 log of 1 is 0 minus 20 log, and this is all base 10 of the square root of 1 plus omega over omega 0 all squared. Okay? And when we are drawing the Bode plot, we tend to draw key characteristic points, يعني key characteristic points, and these key characteristic points are as follows. Let us sketch it here. Okay, so let us look at those key characteristic points. So I found that the 20 log of the magnitude of t is equal to minus 20 log the square root of 1 plus omega over omega 0 all squared. I'm going to look at points where omega is much smaller than omega 0. This will tell me that the expression 20 log magnitude of t is going to tend to what? Is the omega much smaller than omega 0? What happens to this expression here? Pardon, let me change the color. What happens to this expression here?
20 log 1.
Exactly. So هذا بصير 20 log 1. So it tends to 20 log 1, which tends to 0. Okay? And so if I want to draw the Bode plot here, I want to start to draw the magnitude Bode plot, and I'm going to say omega very small. Okay, I'm going to start with a magnitude which is 0 dB, right? And then the second thing which we're going to look at here is if omega is now equal to, or omega, sorry, let us go to the slides. If omega is much greater, let us say now at the much greater than omega 0, what does the expression become? What does this expression become here? With the 1, this tells me that the magnitude of t, okay, 20 log magnitude of t بصير minus 20 log the square root of, would 1 be comparable مثلا أنا if I'm taking 1 plus 1000 لأن omega over omega 0 مثلا for example tends to 1000. Okay, would the 1 matter to me here?
No.
No, so the 1 will disappear from my expression and the square root and the square will disappear. So this is going to tend to minus 20 log of what? Omega over omega 0. Okay, فإذا at very small frequencies, the gain is almost 0 dB for this specific expression. لما أنا عندي 1 على 1 plus s over omega 0. Okay, and when omega is much greater than omega 0, my expression is going to end up being minus 20 log of omega over omega 0. What does this tell me? That this tells me, let me assume that first I am operating at a point x where omega over omega 0 equal to x. Okay. Then the gain will be approximately minus 20 log x. Now, if I am operating at another point, omega over omega 0 equal 10x, then the gain will be minus 20 log x minus 20, what? Minus 20 log what? Pardon me here. 10x, right? What is this equal to? يعني على هاي النقطة minus 20 log x, and at this point it is equal to minus 20 log 10x. What is this equal to? 20 log AB شو بصير؟
بتصير minus 20 log 10 minus 20 log x.
Minus 20 log x. What is minus 20 log 10? Log 10, what is it?
It becomes 1, so we get
1.
minus 20.
So this is minus 20 dB minus 20 log x. يعني this point by how much did it drop? يعني between those 2 points here, if I draw the line between those 2 points here, between here and here, I started at minus 20 log x, and now I have here minus 20 log x minus 20 dBs, right? Is that correct? So moving from x to 10x, what happened here? I dropped by 20 dBs. So the frequency, so therefore what happened here, and let me introduce another slide here. 1 second, new slide. Okay, sorry, I could have erased it. So what happened here is that now, what happens here is if we want to summarize our findings, first we started with T equal to 1 over 1 plus S omega 0. We concluded that if omega much smaller than omega 0, 20 log T is going to be 0 dB. And for omega much greater than omega 0, it is going to tend to minus 20 log omega over omega 0. And we learned that if I move from point x, which is much greater than omega 0, to point 10x, which is much greater than omega 0, okay, I will be operating with a certain slope. And this specific slope that I see here, the drop from x to 10x was how much? Minus 20 dBs. Okay, لأنه when I was at x, I was minus 20 log x, and when I was at 10x, I was minus 20 log 10x, which is equal to minus 20 dB minus 20 log x. Okay, so anytime my frequency increases by 10 folds, anytime my frequency increases by 10 folds, my gain is going to drop by 20 dBs. Okay, so this we call it 20 minus 20 dBs per decade, and we can use it from here on. يعني for a single pole, okay, for a single pole, the gain when omega is much greater than omega 0 is going to drop by minus 20 dBs per decade. And what I mean by decade is that as the frequency increases 10 times, any frequency which is much greater than omega 0, if I increase it by 10 times, I will expect that the gain will drop by 20 dBs at that 10-fold higher frequency. Is this clear? Is this clear? حدا عنده سؤال? Anybody has a question? Okay. So the summary which you can use, the summary which you will be using is as follows. When omega is, هنحط 3 points, point 1 omega 0, omega 0 and 10 omega 0. This I will assume that this here I have reached a value which is greater than omega. And anything below omega 0, we will assume that I am smaller than omega 0. So the gain for this expression here is going to be 0 dBs. Okay, and then after this point, beyond this point, I will drop with a slope equal to minus 20 dBs per decade. يعني هيدا slope هون هو minus 20 dBs per decade. So from omega 0 to 10 omega 0 بالبود plot approximation, which is perfectly linear, at 10 omega 0 I will hit minus 20 dBs for this simple expression. Okay? And in reality, we are approximating the red curve, which for this expression at omega 0, it is really minus 3 dB, but for your purposes, we will always use the approximate linear Bode plot. Okay? So this is the basic Bode plot for the cell, for the basic single pole. Our low pass filter يعني بدون even without gain. The gain is 1. Anybody has any question about this? Did you recall it now? Did you go over the Bode plots in the previous courses?
Yes, went over it in 2019.
Okay. Okay, good. طيب, great. طيب, I will post those slides, and next time if you have any questions, we can go over that, and then we will look at the phase and we will continue through the expressions. And our task next will be to express the transfer function and then try to first draw the Bode plot, second find methods to estimate the effective cutoff frequency, and those methods will keep getting simpler as we